Hello everyone, my name is Yiping Li, and I'm a researcher from Baidu Security. Today, I'm here to introduce a new technique to track the anonymous author of online disinformation. So first, my presentation has 5 sections as shown. The introduction talks about what problem did we solve. The second part is about some previous work we referred to. Method and experiment discuss how we implement our model, and its comparison result with other baselines. Finally, a short summary. So before we get into it, I want to start with a fun fact. Did you know we actually use 100% of our brain power? I thought it was interesting because I have heard many people saying that we only use 10% of our brain. Now back to the theme. So what is the point of this is that I want to show you the existence of false information. From printing to the development of the internet, the information we generated has grown exponentially. While we enjoy the convenience it brings to us, we also have to face the dark side. Here, a study shows that about 3.8 million people spend 144 minutes per day on social media on average. Notice that the data is from 2019, and the status will only go up in 2020 due to the quarantine. From the status, we can see that social media gradually becomes the largest information source. But it also leads to the rise of disinformation, the false information intended to mislead. With the aid of social media, false information has become a serious problem. There is an old saying that a lie will travel around the world while the truth is pulling on its boots. It is a perfect illustration of why false information is so problematic. It spreads out so quickly that you don't even get a chance to stop it. Another study shows that fake news and stories are 70% more likely to be reposted on Twitter. Besides, false information tends to be trustworthy for users because users want it to be true. It is like people saying that you are promoted. You don't know it for sure, but you hope it is true. People are more likely to trust things they want to believe. On the other hand, the purpose of fake news is to attract visitors. Therefore, readers tend to be driven by the emotional impulse, ignoring its authenticity. It is worth to point out that features like top trend and news feed allow fake news to be exposed more frequently. Now you may ask, why would people just make stuff up? What is the purpose of doing this? Actually, they can get a lot. First, fabricating rumors is a public relation move that changes public opinions. Usually, they hire a group of ghostwriters to post online comments or reviews. We call it online water army in China, since their comments are like a float. With those water armies, they can do a lot of stuff, like advertising. For example, if you want to buy shoes, and then you look for some recommendations from others, a review pops up and shows you the top 10 shoes they ranked. It could sound like to the point, but it actually can be a fake review that tricks you into buying their product. Slander and defamation, which used to happen on celebrity and idols. Shifting public attention, which is a classic PR move. Reshaping public opinions. Reshaping public opinion is mostly used in the political aspect, like propaganda. Gaining public attention, which draws attention to themselves so that they can have higher commercial value. And the last, causing marketing turbulence, which will be introduced later. In fact, there is one ultimate goal behind six's purpose, and that is making money. And now, let's talk about potential victims. Fake news actually has a wide impact on us. Anyone can be the victim. Politicians, celebrities, and companies. Those three suffers from deformation and slander mostly. And we consumers would be tricked into a pursuit because of some fake review or fake news. Furthermore, fake news can also bring serious negative consequences, like stock market turbulence. In the past few years, some well-known company has suffered from online short attacks. And you can see from the graph, the stock price dropped sharply due to those short attacks. Moreover, some attackers fabricate fake news about the social influencers so that they can ask for money. Therefore, to protect and maintain personal reputation, brand images, and a healthy cyberspace, it is necessary to track the source of the fake news. However, most fake news and articles are posted anonymously, and it lacks valid information to identify the author. So, tracking anonymous articles is also a challenging problem. Fortunately, it is not impossible. Different people have different writing styles, so we are able to identify some writers by their distinct habits. As shown on the top right, there is two tweeters with two writing styles. Ron Paul is the only candidate who offers us a real choice. That sounds like a senator. It's getting late, so I will be here for probably 2 more hours tops. Actually, I shouldn't read this way. It's getting L, number 8, so I'll be here, number 4. Pop, 2 more. Hers, tops. That sounds like a tweet written by teenagers, right? Or it could be the other way around. But they are definitely two distinct writing styles. And what you see here is that we can kind of guess at their identity based on that. The table on the bottom shows the multiple level of writing styles. For example, different authors may have different preference of word choice. Some people like to use certain adjectives, but others don't. Like my friend who prefers to use hilarious instead of funny. As for the anonymous articles, the more features we collect in writing, the clearer fingerprint we will get. Well, in short, we have discussed the effect of disinformation and some insight on tracking anonymous articles. Let's look at some previous works. So first, the problem of tracking anonymous articles is defined as authorship analysis, and it contains 3 sub-problems as shown on the screen. Authorship attribution takes one text and finds its author from a list of candidates. Authorship verification takes 2 texts, then tells whether the author of the 2 articles are the same or not. Authorship clustering takes a list of text inputs, then organizes the article based on their authors. Lastly, the combination of approach to these 3 tasks is applied to tracking anonymous articles. Surprisingly, authorship analysis is a long-standing problem, and it was initiated by the work of Mosteller and Wallace in 1964. The development of authorship analysis has 3 major stages. In early 2000, a method based on stylistic and content feature was introduced. It requires them to manually extract the traits, so it not only takes a lot of effort but also performed poorly on the test. Character engram was introduced 10 years later, and it has been proved to be the most effective features for authorship attribution at that time. But still, the performance is limited since it involves many high-dimensional matrix manipulation. In recent years, with the breakthrough of deep learning, some researchers proposed a method based on deep learning networks. It turned out to be effective, but only for authorship attribution. Those methods do not apply to authorship verification or clustering. The story does not end there. Although our method is also based on deep learning networks, what's new about it is that it satisfies all three needs in authorship analysis. Let me show you how we did it. First, we were inspired by FaceNet, which is a unified method for face recognition, verification, and clustering. Well, it has achieved a big success in computer vision. Similarly, we propose a unified method based on deep learning, and our model learns a mapping from texts to compact n-dimensional Euclidean space. This mapping embeds a text into the surface of a sphere with a radius of 1 and the center of origin. Basically, our model is like a function which takes text as an input and turns it into a point on the graph. In Euclidean space, the distance indicates text similarity. You can see here there are 4 authors and each of them has 4 articles. Text of same author has shorter distance, vice versa. In the graph, 16 articles are projected to the space. X1 and X2 is embedded to those red dots. Since they are located together, we suppose they are written by the same author. Moreover, to train the model, we define a triplet, a small dataset that contains 3 samples. As shown on the screen, a triplet consists of an anchor, a positive, and a negative. The anchor is the target text, the one we use to compare. The positive is a text from the same author, and the negative is a text from another author. The model will embed these 3 inputs into the Euclidean space. Initially, the 3 texts are mapped into 3 random locations, and the positional relations among 3 points can be categorized into those 3 cases, which is shown on the left. Remember, the distance indicates the text similarity. The first one is when positive is closer to the anchor than negative, which is a case we like to see. The articles from the same author has shorter distance. The second one is when negative is closer to the anchor than positive. We don't want to see that. The third one is when positive and the negative is equally away from anchor. We don't want to see that either. To separate anchor and positive from the negative, we define a triplet loss function, as shown on the left. This loss function aims to let an, the squared Euclidean distance between the anchor and the negative, to be greater than dp, the squared Euclidean distance between the anchor and the positive. For better discrimination ability, we introduced a margin, just like the margin of a support vector machine. In other words, when the margin is 0.5, that means we want negative to be at least 0.5 units further than positive from the anchor. The triplet loss function, which is defined as L, is simply measuring how much further is negative than positive, taking margin into account. You see here is that dp plus margin minus dn. When the loss is positive, that means that the difference is not enough. Otherwise, it means the difference already meets our goal. Therefore, we want the loss to be 0, updating nothing. So there is a max function to set the minimum loss to 0. The sum of the loss of all triplet gives us the total loss. Based on the triplet loss function, we propose a new model architecture, as shown in the figure. The input is a triplet, which has an anchor, a positive and a negative. The output is three Euclidean embeddings, and they are processed by L2 norms, so that they will be mapped to the surface of a sphere. The loss function is a triplet loss, which is able to separate the anchor and the positive from the negative in Euclidean space as we talked about. In particular, the deep network is flexible. Available models are fast text, n-gram CNN, and syntax CNN. Considering the trade-off between performance and the model complexity, we choose the n-gram CNN as our deep network for medium performance and complexity. Besides, we also optimize our triplet selection method. Suppose we have 100 authors in our dataset, and each author has 100 articles. So for each author, there will be 100 anchor, and each anchor has 99 positives to pair. Since there are 99 different authors, we multiply it by 100 articles per person, which is 9900 negatives. The product of those numbers gave us about 10 billion kinds of triplet combinations. That is a huge number, even though we only have 10,000 articles in our dataset. As for the result, we implement two selection methods, and the first one is random selection. Simple but not efficient. Basically, for every possible anchor, we set a top ceiling for the number of positive and negative we select, V and Q respectively. Therefore, the amount of the triplet set will reduce to a manageable size. The randomization ensures that our selection is representative of the overall dataset. But it is not enough for us. Imagine you are climbing over a hill. If you choose a flat road, it might take a long time to reach the top. But if you choose a steep path, the time it takes you to the top is much shorter, even though it requires more work. Similarly, we want the model to learn faster even if it takes more time each epoch. To accelerate model training, we implemented a method called dynamic selection. Firstly, we evenly and randomly divide the dataset into several partitions. For each partition, we select an anchor positive pair, like the random selection strategy, and for each pair, we pick the negative candidate that satisfies the following equation. To put it simple, we filter out those triplets that already meet our goal, which is the first case in the graph. Lastly, we random select one negative from candidate to compose the triplet and throw them into the next epoch. This selection triplet has a positive impact on the overall loss value, which improves efficiency. The fourth part is our experiment, which includes our experiment procedures and results. Firstly, we crowded articles from 8 websites. Then, we organize and clean the raw data, filtering out unwanted information, like incomplete or duplicate articles and author info. Our dataset includes about 130,000 articles from 3,600 authors. We performed comparison experiment on those three major tasks in authorship analysis, as mentioned before. Here is some basic information about our experiment environment. Our GPU is a Tesla P40, and we use the TensorFlow and Keras as the platform for deep learning. In order to explore the effect of the sample size on each model, we rank the author based on their number of words and create 7 datasets that contains authors from top 5 to top 2,000. Also, we select no more than 120 articles per author, and the train test ratio is 8:2 as usual. For authorship attribution, we compared our model with CNN N-gram, CNN Word, and n-gram SVM by measuring the F1 score. DS here stands for triplet SNN model that trained by the dynamic selection, and RS means trained by random selection, of course. You can see here is that our model is over CNN word and CNN gram among all the datasets. Even though n-gram SVM has performed better when the number of authors is 50 and 100, our method has obvious advantage than other baselines when the number of authors is large. Next, for authorship verification. Again, it is determining whether the author of two articles are the same or not. We use the VAL, a matrix introduced in the FaceNet. To evaluate its performance, you can see our model is over the baseline under all datasets and provides higher accuracy on calculating the similarity between articles. Lastly, we use the FB-cubed score to compare our model with logint. Again, triplet SNN DS scored higher in all datasets. The advantage is more significant as the number of authors increase. Here is a graph visualizes the clustering result on 500 articles of the top 2 authors. Blue dots and red dots represent the different author. You can see our method produced a distinct spatial separation, while logint generates a more chaotic image. And that's the end of our experiment. Now, let's wrap up our presentation with a short summary. First, we design and implement the first unified embedding method for authorship analysis. We also designed an effective triplet selection technique. In the experiment, we collect the first Chinese dataset for authorship analysis, and our method outperformed other baselines, especially when the dataset gets large. In the future, we will continue to test our model and optimize the deep learning network and triplet selection strategy. And that's all I have to say. Thank you for your patience. Hope you all have a great day, guys.